A block of mass m kilograms is sitting on a slope of an angle theta degrees. Now, there's no friction acting on the block, so the block could be really anything we want. There's no friction acting on it, so we could consider the block to be like ice sitting on a snow slope. The block will accelerate down the slope, and that acceleration will be caused by an unbalanced force acting parallel to the slope. And that's our job, to find an expression for that force which is causing the block to accelerate down the slope, or the force which is pulling down the mass parallel to the slope. Now, to help us do that, we have to construct a set of axes round the block, and the best way to do it is to construct them like this. So this axis here is the one parallel to the slope, and this axis here is the one perpendicular to the slope, and that will help us in fact work out the force which is acting parallel to the slope. That's what we're after in the long run. Now, in order to find the forces, we must put the forces in which is acting on the block, and the first force acting on the block we consider is the weight of the block, and that acts straight down, almost like a plumb line to the block. There's the weight force vector acting straight down. Now, there's another force acting on the block, and that is due to the reaction force of the block on the surface. The block will be pressing down the surface, and the surface will be pressing up on the block. It's called the normal reaction force, and that is perpendicular to the block as shown by that vector. So there we have it. We have the two forces acting on that particular block. Now, what we're interested in is to find the component of the weight which is going to be parallel to the slope. Remember, there's no friction force acting on the block, so therefore there's no backward forces acting on it. Now, to do that, we must set up a little rectangle around the weight vector. So if we do that, and we draw another line, we have got a rectangle round the weight vector, and then we can work out the components of that. So, for example, the component of the weight, which is going to be perpendicular, will be represented by that vector here, and the component of the weight parallel to the slope will be represented by that vector there. So we have our triangle of forces, very, very clear indeed. One thing's missing though. What is the angle between the weight vector and its perpendicular component? Well, we get that from the angle of the slope. It's a mathematical formula which shows you that the angle of the slope is in fact that angle in here. So we can just put the same angle and represent it in there. So there we have it. We have got our triangle of forces. We've got our angle. It's a right angled triangle. There's a right angle there. And we can go ahead and use some of our trig expressions to try and calculate the components of the weight. Well, the first one I want to find is the component of the weight parallel to the slope. That's the part shown now. Now we can use our sine law to get that answer. Sine theta of that triangle is going to be the opposite side divided by the hypotenuse of the triangle. Now the opposite side is shown to be the weight, the parallel component of the weight down the slope, that's the one we're after, divided by the hypotenuse of the forces triangle, which is the weight itself, W. So we have an expression, sine theta is going to be equal to the weight parallel to the slope divided by the weight. And we also know that the weight is always equal to mg, so we can rearrange this to give us that the weight component parallel to the slope is going to equal to W sine theta, and we know we can replace the W by mg, so we have mg sine theta. So that's going to be the force which is going to be acting parallel to the slope, and we can actually copy that vector. Remember, we can slide vectors up to another position, and there is the force which is acting parallel to the slope, which is causing the unbalanced force which is going to cause the mass to accelerate down the slope. It's a very famous expression, that one, and we can write it out again. We can say that the weight parallel to the slope is going to be equal to mg sine theta, and it always acts down the slope. So that's our main rule. Some people drop the weight parallel and just put down the force down the slope, or the force parallel to the slope downwards is mg sine theta. So if you look at that very carefully, you can see that the force acting down the slope is mg, and it's diluted by the sine theta. So we're almost getting a slope to be like a diluter of gravity. So that's our key expression. The force acting down the slope is going to be mg sine theta. Now, what about the other component, which we'll do in black? Well, the other component is the perpendicular component of the weight acting this way. Now, there's no motion of the block in the perpendicular direction. There's no unbalanced force, and that must mean that the normal reaction force N must be equal to the perpendicular weight. So we have then the normal reaction force must be the same size as the perpendicular weight component. Now we can use our trig once again to find the component of the weight which is acting perpendicularly. And we find out if we use our cos expression, cos of the angle theta is going to be equal to the adjacent divided by the hypotenuse. In this case, the adjacent is going to be our perpendicular weight divided by our weight. So if we put this down the following way, cos theta is equal to perpendicular weight divided by, and the weight is going to be mg. Then what we can do is cross multiply and get the expression for the component of the weight acting on the block, and that's going to be mg cos theta. And that's going to be exactly equal to the normal reaction force. So the normal reaction force is going to be mg cos theta. And that's the other component of the weight which we'll mark in green. So we now have the component of the weight acting down the way, and we now have the component of the weight acting parallel to the slope like that. And it's this force here which is causing the acceleration of the block down the slope, because there's no friction force acting on the block. The force acting down the slope, parallel to the slope, is equal to mg sine theta.